Hello everyone, I'm Paul and today we're solving problem 1912, Design Movie Rental System. This is a hard one, so next I will show you my thought process step by step and then we'll go with the code. This is a really long description and I think this is part of the challenge. You need to be able to filter information that's not important and keep only the important stuff. So we need to implement the movie rating system class. And first we have a constructor, we need to build some data structures, and then we need to implement 4 methods: search, rent, drop, and report. Usually when I see something like this, I take notes to keep track of my thought process. So let's start with search. Here we need to find the 5 cheapest shops that have an unrented copy of the given movie. We are giving the movie as an argument. So we are given a movie and we need to return the cheapest 5 shops. So we will have an array with shops and this looks a lot like a map. So this is our first observation. Now we need to return the cheapest 5 shops. What this means is shops should be sorted by price in ascending order. So for each shop, we are including the price also. And we can store each of these as a tuple. And here it says that in case of a tie, the one with the smaller shop should appear first. So we are sorting prices in ascending order and we are sorting shops in ascending order. And we can do this automatically with a sort list. So in this map we will have every movie as a key and the value will be a sort list with tuples with price and shop for the corresponding movie. And this is how we can sort this automatically by price first in ascending order and by shop next in ascending order also. So when we call search with the movie M, for example, we go to the corresponding movie, meaning here, and we take the first 5 elements here and we return the shop for the first 5 elements. Now let's go with this method, report. Here we need to do something very similar. We need to return the cheapest 5 rented movies. So we can have some data structure with rented movies. For now, let's say this is a list. And we need to return each element in the form of shop and movie. So here we can have tuples also. And in these tuples, we need to include shop and movie. Now remember, we need to return the cheapest 5 rented movies. This means that we also need to include their price. And here it says that we need to sort this by price first in ascending order. And if there's a tie, then we use shop. We need to sort this in ascending order also. And if there's still a tie, we need to use movie also in ascending order. And this happens to be the default order for sort lists. So here we are using another sort list. And this will automatically order tuples in this order. First, we sort every tuple by price, then by shop, and then by movie. So basically we need these 2 data structures. We are keeping track of the movies that we have up here, and we are keeping track of the rented movies down here. Finally, here we have 2 more methods. We can rent a movie, so we need to remove the corresponding movie from here and add the corresponding movie here. And we can drop a movie. Here this drops off a previously rented copy of a movie. So in this case, we need to do the opposite. We remove the movie from here and we add it here. Now the question is, how can we remove movies from here and here efficiently? And we have a method in sort lists which is discard. And here we can use a key following this format if we want to remove something from here, or this format if we want to remove something from here. Now when we call rent and drop, we are given a shop and a movie, but we are not given the corresponding price. So we can't form this key and we can't form this key. We need to find an efficient way to get the price of a movie if we know what is the shop and the movie. So we can have another data structure, which is a map where every key is a tuple with shop and movie, and every value is the corresponding price for this combination of shop and movie. Up here, it says that each shop carries at most one copy of a movie. So we know that this combination is unique. So this will be a key for our new map, and the value will be in the corresponding price. So now when we call rent with some shop and some movie, we can go to this map to get the corresponding price of this combination. And once we have this price, we can build this key or this key. Let's say we call rent, so we need to build this key. First, we take the given shop and the given movie to get the price. And with this, we build a tuple with price and shop. And now we are checking in this movie, meaning in this movie, if we have this tuple. We have it right here. So with discard, remember this is a method for sort lists, we are using discard to remove this in log and time complexity. And after removing this from the movies that we have, we can add the corresponding movie to rented. So we can build a tuple with this format. First we have this price, then this shop, and then this movie. And now we add this tuple here to rented. If we call drop, we do exactly the opposite. First we build this key and we drop this movie from rented, and then we build this key and we add this tuple here in the corresponding movie in the map for movies that we have. So this is basically the entire approach. As you can see, we need only 3 data structures, and this is more sort of like a reading problem. So with this in mind, let's go with the code. First, we start up here and we are building our 3 data structures. Self.movies, this is default dictionary with a default value of sort list for every key. And then we need a data structure to store the prices for every combination of shop and movie. Remember, every shop and movie is a unique value, so these are the keys, and this is initially an empty map. Now, self.rented is a sort list, and now we can iterate entries. So for SMP in entries, self.movies at the current movie dot add, and here remember we are adding tuples with price and shop, and self.smp at the unique value, which is a tuple with shop and movie. This is equal to the current price. So now we can move here to search, and here we have an empty array initially. We are returning this, and here in between we say n is the length of self.movies at the given movie, and for I in range 5, if I is equal to n, we just break this loop, else result.append self.movies at the given movie at the current index at 1. So just to be clear, here we are adding the corresponding shop. Okay, this is the required format. So now we are building rent, and here first we need to take the price for this unique combination of movie and shop, and we have our data structure to do this. So price is equal to self.smp, and this is a tuple with shop and movie. So now we have the price, and we can build our keys to discard the current movie from the movies that we have. So self.movies at the given movie dot discard. Remember, this runs in log n time complexity, and we are discarding the combination of price and shop. This is the required format for sort lists in movies. And now we need to add the movie to rented. So self.rented.add a tuple with price, shop, and movie. And now we are doing something very similar for drop. We are doing the opposite actually. So we can just copy this we get the price in the same way, and then we need to add the movie to movies, and we need to discard the movie from rented. Finally, we are building this method report. So we are doing something very similar as before. Result is an empty array. We need to return result, and here in between n is the length of self.rented. And for I in range 5, if I is equal to n, we just break the loop. Else we add to the result an array with 2 elements, shop and movie. So self.rented I, this is index 1, and next for movie self.rented I 2. Just to be clear, this is, we are adding arrays with shop and movie. So this is it for the code. I think this is right. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Time complexity for this part will be big O of e times log e. Remember that operations for sort list require log n time complexity, and space complexity will be big O of the amount of entries. Here, time and space complexity is big O of 1. Here it's also big O of 1. Here space complexity is big O of 1, and time complexity is log n. Remember that these operations run in log n, and here it's the same. So this is it for the code. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.